All right, so good afternoon, everybody, and welcome to the Iowa Learning Farms 2024 Conservation Webinar Series. I'm John Dahlem. I'm a research associate with Iowa Learning Farms, and I'm filling in for the rest of the team today as they take care of some important work. We're thrilled to have with us today Dr. Peter Moore. He's an adjunct assistant professor in the Department of Natural Resource Ecology and Management at Iowa State University. Dr. Moore is a geomorphologist who studies the erosion, transport, and deposition of sediment across the landscape with a focus on river corridors. Pete will be talking with us today about understanding phosphorus exchanges in rivers and floodplains. And so we think this is going to be a very interesting topic today. We hope that you have a lot of questions. We'll do a Q&A at the end, as always. So anytime that you have a question, please go ahead and feel free to put that in chat. We will get to those questions at the end of the presentation, okay? So at this time, I'll go ahead and I'll hand it over to Pete. Pete, the floor is yours.
Thanks very much, John, and thanks everybody for joining us. Thanks for having me. I appreciate the invitation from Iowa Learning Farms. I'm going to dive right in here. I've seen quite a bit of research in the past, and even some recent Iowa Learning Farms webinars that make the case that bank erosion is an important input of phosphorus as a non-point source of phosphorus to our surface waters. And I don't dispute this. This is really important, and it's something that my research group has put in quite a bit of time to try to quantify, to try to understand the various inputs and outputs of phosphorus to the surface waters in Iowa as well as the surrounding region. As a geomorphologist, though, my interest is particularly in sediment transport. Fortunately for me, I guess, sediment is a really important host for phosphorus, and a lot of the phosphorus that travels is input into our surface waters and travels with them downstream is attached to particles or is a particle on its own. So if we follow particularly fine sediment through the river corridor, we'll have a pretty good sense for where the particulate phosphorus is going. But as a geomorphologist, I'm really interested in not just what comes into the river, but also what leaves the river. So where does phosphorus-laden sediment go after it enters the river through bank erosion? That's really what I'm after in the research, although I'm interested in both directions of exchange, river to the landscape and landscape to the river. But we're going to focus on trying to quantify those today. Before I get too much farther, I just want to define for you kind of the scope of the different processes that we're interested in. And I'm going to define the riverscape as the portion of the landscape that surrounds us that's in the river valley, in the valley bottom. And that includes things like the floodplain, but also the river and its banks and bed. And all of these can take part in and play a role in the exchange of sediment and phosphorus between surface waters and the surrounding landscape. So I'll use the term riverscape to kind of encompass all of that or capture all of that. The meander belt is this portion of the riverscape where a lot of relatively rapid exchange is happening, and I'm a geologist, so when I say rapid, I'm talking about decades to centuries. That's really quick, geologically speaking. But the river bank erosion that we've been talking about, and that's covered so much in the literature, and that if you go back a couple of weeks to Andrew Margonaut's Iowa Learning Farms webinar, he gave a great summary of some of the research from the region about phosphorus inputs from bank erosion. That's happening in these cut banks here. But additionally, in addition to those inputs of sediment and phosphorus from cut banks, we also have to think about places where that same sediment and phosphorus that's been input from a cut bank, where that can get deposited again within the river corridor. And that's something that my research group is really focused on. So if we try to kind of call out all of the processes that can result in inputs of sediment and phosphorus into the river, but also removal from the river into the riverscape. Some of those inputs include bank erosion, which we've already mentioned, but also bed erosion if we're in a river system that's having a tendency to downcut or in size into its river valley bottom. And floodplain stripping is a process that has been documented in some rivers and is probably not particularly important in Iowa, but that would involve in high magnitude flood events, the top of the floodplain being eroded away. Sediment and phosphorus can also be removed from the river or transferred out of the river into the riverscape by lateral bar accretion, vertical floodplain accretion, and oxbow filling. And I'll explain what I mean by those accretion terms here in just a second. If we look in a cross section of a typical alluvial river, we see bank erosion happening here on the right side of this illustration. If that happened with no other response from the riverscape, the channel would just get wider and wider and wider over time. But that doesn't typically happen. Usually there's deposition on the opposite bank that accompanies bank erosion. And so that advancing bar on the opposite side of the river is advancing through lateral accretion of sediments. And if lateral accretion and bank erosion happen at about the same pace, the river maintains a constant cross-section size over time. If you look at one of those advancing point bars across from an eroding bank, they typically become vegetated over time, particularly at higher elevations above the sort of low flow runoff event elevation. And that vegetation can help to slow down floodwaters and promote the settling of fine sediment. So once vegetation becomes established on a laterally accreting point bar, we start to deposit on top of that stuff these vertical accretion sediments that are typically finer grained, sometimes rich in organic matter, not only because of inputs of the vegetation that is growing there, but also transport from upstream. If we look at an image of kind of a close-up of this transition between lateral accretion and vertical accretion, you can see the difference in the types of sediments. Lateral accretion is what you would think of as the sandbar sediment. So it's often very sandy, sometimes pebbly. Doesn't tend to be terribly rich in phosphorus, but it forms the foundation of new floodplain that can accrete over time vertically once that vegetation gets established. So on top of this lateral accretion sand, you see vertical accretion deposits that are much more rich in organic matter. They're loamier, and they also tend to have considerably more phosphorus in those sediments. In a much more mature floodplain setting, this is an eroding cut bank in the Nishnabotna River that I'm going to be talking about in a few minutes. You can see that the upper couple of feet of a lot of these floodplains is formed with vertical accretion deposits. So again, this is just layers upon layers that are laid down one on top of the next of relatively fine loamy sediment that's relatively rich in organic matter, and it sits on top of a foundation of those lateral accretion deposits. And these are within the meander belt. These are recycled over time, over and over again, and moved slowly downstream, quickly during flood events, but then left on the riverscape for long periods of time in between those events. So if we look at these transfer processes for sediment and phosphorus within the river corridor, I'm going to focus in on the ones that are shown in yellow here because they're probably the ones that are dominant in terms of the volume or mass of phosphorus that they deal with in the study area that I'm interested in. So bank erosion, we've already mentioned that. That's clearly a really important input to the river from the surrounding riverscape. The removal processes could involve these lateral accretion deposits that tend to be those sandy point bars, vertical accretion on top of them, and then vertical floodplain accretion on more mature floodplains that may be distal from the channel itself. I'm going to talk about these through the lens of sort of a multi-year study of the Nishnabotna River. The Nishnabotna River, if you're not familiar with it, is a relatively large river system in southwestern Iowa. Its watershed is over 7,000 square kilometers, and most of that watershed is intensively cultivated with row crops. It's in the deep loess region of the southern Iowa drift plain, so the soils are mostly composed of either loess or alluvium derived from the past erosion of loess and then left in the river floodplain. There's over 2,000 kilometers of river channel here, and I'm talking about river channels from Strehler order 3 and up. We're going to kind of set aside, and we can talk about later if you're interested in, but we're going to leave aside the headwater channels, and I'll explain why that is later. I've got a few boxes in here in this map showing some particular parts of the Nishnabotna watershed that we've focused in on. In some past work with some partners over at the University of Iowa, we've seen that there's about, on average, 2 million kilograms of phosphorus that are exported annually from the Nishnabotna River, and that most of that phosphorus comes in the form of particulate phosphorus. So again, if we follow the fine sediment that tends to be the host for a lot of this phosphorus, we're likely to also be following the phosphorus itself. And if we're interested then in addressing that nutrient load and thinking about ways to reduce it, we should be thinking about ways to understand the transfers of that fine sediment between different components of the riverscape. So again, back to this list, I'm going to summarize this into 3 different components: bank erosion as a key input from the riverscape to the river, and bar accretion, including both the lateral and vertical components, as well as vertical floodplain accretion outside of the meander belt. Those are going to be the 3 different components that we look at. And if I were to give you all of the details that you would probably need to have in order to, fully grasp the research processes that we went through to get the result that I'm going to present, it would take forever. So I'm going to really vastly oversimplify a lot of this, but I'm happy to answer any questions that you have about some of these little components of the study. I'm going to try to summarize each of these components into mean annual phosphorus exchanges that are scaled to unit channel length. So in other words, we're going to quantify the inputs and outputs of phosphorus to the river and the riverscape in units of kilograms of phosphorus per meter of channel length per year. And on the bottom left of this slide, you see an equation that I've set up to try to sort of summarize the inputs and outputs. Delta on the left is sort of my total change in the total net transfer of phosphorus within the riverscape, and E is that bank erosion input. B is bar accretion, including both the vertical and lateral accretion, and then F is the floodplain deposition. So I'm going to walk through a couple of studies then that have attempted to quantify each of these independently. We'll add them all together and see what we get. The main takeaway then from this is that if that delta value is a positive number, then the riverscape is serving as a net source of phosphorus to the river and to export of phosphorus from that river system. Now, if the delta is a negative number, then the riverscape is acting as a net sink. That is, it's trapping more phosphorus in the terrestrial part of that riverscape than it's inputting through bank erosion. So we'll start with the bank erosion component. This was the assignment of a master's student who completed his study in 2019. Forrest Williams got an MS in environmental science. And basically his research question was how much phosphorus enters the Nishnabotna River when its banks erode. And he was particularly clever and created a remote sensing tool called the Aerial Imagery Migration Model that takes imagery from across the study area, and it classifies every pixel in the image as either water or not water. That's a pretty widely used scheme. It's called the NDWI, or Normalized Difference Water Index. But if we have that from multiple different years, and we can sort of compare what was water in one year and what was water in another year, and if we ensure that there wasn't a flood in one image and not a flood in the other image, we can overlay those classified images on one another. And if we see that there was water in one image and not water in another in a particular place, we can infer that there was deposition that happened between those two images. And likewise, if there was no water and then there became water, then we can classify that as erosion. So the difference detection between those classified images allows us to identify areas in the riverscape where erosion and deposition happened. And if we overlay the resulting data on elevation data, we can convert those sort of areas of erosion and deposition to volumetric estimates of erosion and deposition. And here's an example of the output of just a little piece of that from that Red Oak Reach, just south of Red Oak and the East Nishnabotna River. So we're superimposing that imagery from multiple years and detecting erosion, which is shown here in red, and deposition shown in yellow. I'm going to focus mainly on the erosion part because we've learned since Forrest finished his study that the deposition detection in here has some significant limitations, which we have overcome with our subsequent studies. So if we combine that remote sensing process with some sampling of the material that's actually out there, and we characterize the total phosphorus concentration in the sediments that are being eroded from the banks, and then measure their bulk density, we can convert a volume of eroded bank material into a mass of phosphorus that's input through that bank erosion. So, long story short, we have a result. The result for all of the channels of third order and higher within the Nishnabotna watershed, including both the west and east Nishnabotna rivers, is about 0.42 kilograms of phosphorus per meter of channel length per year. Okay, so we can start to put in numbers into this equation. 0.42 is substituted in for E in that first position on the right-hand side. For the other two components, we've taken advantage of a really cool data set that we have access to in Iowa. And if you're not familiar with LIDAR, this is light detection and ranging, and there is a really powerful technology for rapidly acquiring really high resolution elevation data from across the landscape. And we have in Iowa a data set, a LIDAR data set collected statewide between 2008 and 2010. And we also have a data set collected in about 2020. So we have two different snapshots of really high resolution elevation across the entire state from two different time periods. If we can compare the two, we can find areas on the landscape where there's been net erosion or net deposition. And that process of comparison between two different point clouds resulting from LIDAR or another process that produces point clouds, we can call that geomorphic change detection. We use a particular algorithm when we do this called M3C2. So I'm going to show some results in the near future that show this M3C2 distance, which is basically how much elevation change results from either erosion or deposition. I have this figure in here just because I think it's a really neat demonstration of how this looks. You've got a gully here from a study done in Croatia a couple of years ago that's been analyzed with this geomorphic change detection using the M3C2 algorithm. And you can see all these areas in the gully in red where there was some erosion between the two different point cloud acquisition campaigns. And in blue, you see areas of deposition. So we're going to use the same general idea or same process in the Nishnabotna River corridor. Oop, wrong way. The first of these two studies was done by Tanner Lambert. He focused on bar accretion within the meander belt. Again, on the Nishnabotna River, although we were zooming in on just particular meander bends within the West Nishnabotna River between Hancock and Henderson, on that about halfway up that main stem of the West Nish. So Tanner earned his master's in geology in 2023, and his study involved first identifying meander bends all the way up and down that reach of the river, and he cataloged both meander bends that had bank stabilization structures on them of any type and those that did not. And he chose 3 of each type to compare using this M3C2 algorithm. So you can see on the left here, this is an example of one of the study areas. This is Botna Bend Park, just outside of Hancock, on the northern end of this part of the West Nish. And I've highlighted here the bank stabilization structure that protects the railroad and part of the Botna Bend Park on the southern half of that study area. And then there's a couple of meander bends to the north that are unstabilized, or there's no bank stabilization structure on them. And if you compare, or if you look at the results of the M3C2 distance analysis on the right-hand side, you can see areas where banks have eroded in red and places where bar deposition has accumulated sediment in the blue. That can be kind of difficult to kind of pick out the details, so I'm going to zoom in on just that, those areas, and overlay only depositional areas on top of the aerial photo of this same area. So you can see deposition ranging from 0 to 2 meters in vertical deposition. Now across all 3 of his unstabilized bends, there was an average of about 0.76 kilograms of phosphorus per meter per year accumulated, and on bends that had bank stabilization structures on them, the point bars accumulated only a half kilogram of phosphorus per meter per year. Relatively small sample size, but we think that these bends that were selected are relatively representative of the bends present on the West Nishnabotna River. Take-home messages from that study are that we found that stabilization sort of switches off the lateral accretion component of sediment accretion on point bars. So having a bank that's stabilized, a cut bank stabilized, reduces the amount of sediment that can accumulate on the opposite point bar simply by shutting off its ability to create the foundation for more sediment to accumulate. So I fudged some numbers here because the point bars don't occupy the entire channel length. So I've scaled them to what I think is an appropriate representation of the channel length that it represents. And for this bar accretion term, we get values between 0.25 and 0.38 kilograms of phosphorus per meter per year. So I've entered that now into that equation on the lower left. Last component here is that floodplain deposition component, and this was the responsibility of another master's student, Kelvin Aduba, who just successfully defended his thesis last week, almost exactly 1 week ago. And he selected an area of the West Nishnabotna River. This is about a 20-kilometer long segment of the West Nish, where he randomly identified 150 places to go out and take samples and do some observations in the field within the 25-year floodplain in that segment of the river. That means the portion of the floodplain that is on average flooded about once every 25 years. It turns out that 2019 was one of those events in this area. So there had been a flood event that reached this extent in this segment of the river between the 2 LIDAR campaigns that we took advantage of. So on the right-hand side, you can see the elevation change raster that shows the M3C2 distance. These are the same results that we saw, or the same type of results that we saw in the previous results, showing deposition areas in blue and erosion areas in red. I know you can't see the details in there, but I mainly want you to take away a few things. We see a lot of pale colors indicating that these are relatively small magnitudes of erosion and deposition. But one of the things that if you're an astute observer of these maps here, you'll see a lot of areas of red that correspond to areas that are shown in the land cover map in the middle as forest. And we kind of anticipated this as a potential problem because the laser that acquires LiDAR data can sometimes have a difficult time penetrating through a tree canopy, even when there's no leaves on the trees. And so we expected there might have been a little bit of additional error introduced into the measurements in those forested areas. So we also acquired some additional data using dendrochronology and measuring the depth of tree root burial within some of the forested areas of the floodplain. And the main thing I want you to take away from this is that this bar graph here on the right-hand side in the left, or sorry, the box plot on the left one, we've got dendro estimated deposition rates that are all positive. This is for 15 different trees. And whereas in the M3C2 result there, they are both positive and negative, indicating both deposition and erosion. Positive deposition rates, by the way, mean net accumulation of sediment. So the fact that all of our trees indicated positive deposition rates suggests probably that those negative deposition rates, or the reds that corresponded to erosion within the forest, are probably suspicious, and we should take those results with a grain of salt. And I will do so here in a second. So the general result overall, and again, I'm oversimplifying a lot and skipping a lot of the details here, but the result of floodplain accretion is that net deposition was about 0.22 kilograms of phosphorus per meter per year if we take at face value the results that we get, including forest erosion. But if we eliminate all of the forested areas from consideration, our gross deposition then is just 0.44 kilograms of phosphorus per meter per year. And of the different land cover types that we identified and that were sampled, grass was shown to be the most effective at promoting deposition, even though the sediment that was deposited in the grassy areas tended to be more sandy and have less phosphorus. The sheer volume that was deposited on those grassy sites made them very important sinks for phosphorus. I will point out a really important thing here is that I don't think we would have measured any accumulation had there not been a flood in 2019 that accessed the floodplain, right? So this floodplain sink is non-existent if the river does not have access to flooding its floodplain, or to inundating its floodplain and transporting sediment and phosphorus out onto the floodplain where it can distribute it broadly. Okay, so here's our result from the floodplain deposition term. The values range from 0.22 to 0.44 kilograms phosphorus per meter of channel length per year. If we sum all of these terms up on the right-hand side, we end up with a negative number, negative 0.29 kilograms phosphorus per meter per year, with values ranging from negative 0.4 to negative 0.05. Notice those values, even that range of conservative values, they're all negative, meaning that the riverscape is a net sink for phosphorus, at least in our study area. More phosphorus is coming out of the river and going out onto the riverscape, the terrestrial portion of the riverscape, than is coming in through bank erosion, according to this analysis. All right, I flew through a lot of information really fast, but I want you to take home a few things, a few concepts and ideas. First, we did show with forest study that bank erosion is a significant source of non-point phosphorus to surface waters. When we compared the amount of phosphorus that was coming off of banks in just those third order and higher channels, in the Nishnabotna watershed, it amounted to 46% of the total load that had been previously estimated for the entire watershed. So it's a really important source there. However, deposition within the riverscape is also an important non-point sink of phosphorus. So we have to be thinking about that two-way transfer of material, including phosphorus, between the surface waters and their surrounding terrestrial landscape and the riverscape. Note, though, that access to and the longevity of the non-point sink represented by bars and floodplains requires connectivity, and it requires that there's the dynamic change that is natural in these meandering and migrating river systems. So with that, I'm going to bring this to a close and just acknowledge the funding sources. Some of this project was funded by the Iowa Nutrient Research Center, Hungry Canyons Alliance, the Leopold Center, as well as McIntyre Stennis Capacity Fund. A lot of students and scientists contributed to this work, and I am acknowledging all the ones that I could think of here in the bottom right. So with that, I will move on to the next slide.
Okay, thank you so much, Dr. Moore. Just as a reminder to everyone, if you have any questions, please put them in the chat. Those will go directly to me, but I will ask them to Dr. Moore here in the Q&A session following these next few slides. So if you have any questions, that's the system that we use. Type those in chat and I'll see those. We have a number of questions I'll be getting to here in a second. So if you watch today's webinar and would like to receive a CCA CEU, you are invited to email Elena Whitaker. That's Elena, ALENAW, at iastate.edu by this evening at 5 p.m. Central Time with your name and also the name you use to enter this webinar, and Zoom if you're using a different name than the name you would otherwise use, and then also your CCA number, and we will get that submitted for you. Pete, if you could please go to the next slide. Great. Our demographics survey. So if you've attended a previous webinar and have completed this survey, thank you. If you have not, we ask that you please help us track this information as a USDA-funded program. You can access the survey by going to iowalearningfarms.org/survey or by pulling out your phone right now and scanning that QR code on the screen right there. You only need to submit one response in the 2024 calendar year. So if you've already done this, thank you again. And then the next slide, if you don't mind. Yeah, and our next presentation is going to be Drainage Showdown, which pipe style drains faster? And that's with Asan Ghani, Associate Professor of Biosystems and Agricultural Engineering at Michigan State University. And then one more slide, I think. Yeah, and so finally, like all of our webinars, today's has been recorded. It's going to be uploaded soon to ILF's webinar archives. You can find all of our webinars there in one place by visiting our website at iowalearningfarms.org/webinars. And by request, we've also uploaded all of our webinars to YouTube, and you can find them sorted by year and topic in playlists on YouTube. So with that, we've had a series of questions come in for Dr. Moore, and I see the chat flowing and a few more. So I'll go ahead and start to send a few questions your way if you're ready.
Yep.
Okay. And I know some of these pertain to specific slides, so we may need to move around, but got a question here. I have planted, I'm sorry, I don't know how to pronounce this, Austree willows along each side of the stream bank for 1 mile. I have stopped all bank erosion. The Austrees form roots visible right in the stream. Would these trees also pull out the phosphorus in the stream water and use it for plant growth?
Great question. I'm not sure that I'm the best person to answer that. I'm sure that that willows will draw some phosphorus. Although if they also die and decay and are swept away in floodwaters, that same phosphorus will be contained in the organic material of the plant itself. If they do succeed in stabilizing that in the long run and are fully buried by sediment over time, then sure, that's probably incorporating or kind of locking that phosphorus in place, which is great. So I don't know that I can really answer how much question, but I'm certain that they're likely not doing any harm to the phosphorus.
Okay, I've got another question here that asks, have you worked with any local sewage districts or related authorities to implement an adaptive management plan to focus on the reduction of phosphorus and improve water quality?
The short answer is no. I'm not certain what you mean by an adaptive management plan. I am aware that there are like nutrient trading programs in places where point sources might sponsor the um, stabilization of stream banks, for example, that are perceived to put a lot of non-point source phosphorus or nutrients in general into surface waters as a way of kind of offsetting their loading. But I would hesitate to answer anything to give you any answers about adaptive management. I would hope that all of these uh, kinds of efforts are adaptive in their management, but I'm not participating in any particular program.
I've got a question here asking, how does the LiDAR change detection method work with stream bed elevation changes? For example, are you able to detect sediment accumulation in pools in the stream?
Yeah, it's a great question. Again, the short answer is we can't do that. The LiDAR doesn't see, at least the product that we have available to us in Iowa doesn't see through the water. So we're only looking at the exposed sediment and bars and banks when we look at LiDAR change. Um, and fortunately or not, the LiDAR acquisition tends to happen in leaf-off periods during the year, and the river flows tend to be also relatively low during those acquisition periods. Excuse me. So a lot of these parts of the riverscape where we think sediment deposition, uh, longer term sediment deposition is happening, are going to be exposed at that point, and we can see change in those settings. But as far as detecting geomorphic change in the riverbed underwater, that's something that we don't yet have um, when I say we, like I don't yet have the data source to be able to address that at any significant scale.
Got a question here that asks, how hard was it to get access from private landowners to conduct the sampling?
Um, Hours were put into cold calls to landowners. I'll acknowledge that. I will also tell you the dirty secret that in Kelvin's study on the West Nishnabotna, part of the reason we selected the reach that we did was that there's maybe a half dozen landowners who own more than half of uh, that stretch, the land in that stretch. So it amounted to calling 5 or 6 different people, and we got access to hundreds of acres of land. But honestly, working in private lands and properly requesting access to those lands for research can be really tricky and really time consuming.
I've got another question asking, are there similar studies focusing on overland non-point contributions to phosphorus load?
Yes, there are. Uh, the there's it's tricky to do that at scale. If we're talking about the scale of the entire Nishnabotna watershed, the idea that we could do a good job of measuring both the mass or the volume of eroded material and where it's deposited, and characterize the phosphorus concentration in that same sediment. That's really tricky to do even at the field scale, but it can be done. More often when folks are interested in trying to address these questions on larger scales, we're using computer models that try to sort of estimate over large areas the erosion and potential deposition of those same materials, and then some scaling parameters, things like sediment delivery ratios, and those can be pretty tricky to quantify properly as well. So the answer is the short answer is yes, there have been efforts, but it's a really tricky thing to constrain well.
I have a question asking, do you expect the rate of erosion slash deposition to stay largely the same in the short term, or would you expect the rate to increase with more erratic weather events?
Yeah, it's so erosion is a for the most part, it's a process that has thresholds. If you have very, low magnitude events all the time, they're only going to accomplish a little tiny bit of erosion relatively slowly. But if you have, highs and lows, if you get periods of drought that expose a lot of soil to weathering, a lot of, stream banks to weathering, and then you come through with high magnitude flood events, that's going to do a lot of geomorphic work. It's going to move a lot of sediment. And so I think my answer would be more frequent or more higher magnitude events separated from one another with periods of drought is probably going to make erosion happen faster. So
Okay, another question here. With the combination of erosion slash deposition rates and dendrochronology, have you been able to estimate ranges of quote unquote residence times for floodplain sediments and down valley meander migration rates?
uh, great question. That sounds like somebody who studied some geomorphology. It's that's on my bucket list for something that I'd like to do in this study area. We've done some kind of turnover time estimation in different river corridors, and it's very spatially variable. I'll say that. Some of the variation and spatial variation has to do with differences in kind of the composition of floodplain materials, the presence of valley confinement or terraces, things like that are going to make it quite variable from place to place. But that's definitely something I'd be really interested in pursuing.
Someone asks, do you have any thoughts on how riverscapes with different levels of riparian vegetation slash buffer widths may differ in terms of being sources or sinks for phosphorus?
I mean, if you just look at our results with at Kelvin's results with the three different cover types, and just extrapolate from that, which is not safe, but if you extrapolate from that, I would think that if we had grassy buffers everywhere, we'd trap more sediment and phosphorus than we would lose, and do that consistently. With tall banks, like some of the ones we're seeing in the main stem Nishnabotna rivers, grass itself, if it starts getting cut into, isn't going to stabilize the banks as well as, some other alternatives, just because the banks are so high and the cohesion that particularly cool season grasses offers doesn't extend 3 meters down necessarily. But if we had graded grassy buffers on banks that aren't being undercut, I think they would do a really good job of stabilizing those bends and trapping sediment that comes their way.
Someone asks, do you plan to study the first and second order stream network?
I'd love to. One of the things that is important, though, about this system is that, um, at least on the scale that we're analyzing, for example, the LiDAR geomorphic change, it's extremely data intensive, and we struggle to get even 10 miles of river analyzed in one sitting because the amount of memory that we have access to do the analysis is limited. And as soon as we start going upward into the watershed, I think our best approach would be to select a few representative first and second order basins and do an analysis just on those. One of the problems, though, with analyzing some of these first and second order areas is they also tend to be, places where they're steeper, particularly in the Nishnabotna Basin, where some of those first order channels are gullies, and they're also, as a consequence, they're also often just wooded. And so the problems that we had with the LiDAR fidelity in forested parts of the floodplain are going to be sort of compounded by the presence uh, of forest covering these gully walls. So yes, I'd like to try to do this, but I think we're going to need to um, try something a little bit different with our geomorphic change detection.
Okay, I've got a few more questions here. Someone asks, in many situations, rock is needed to stabilize the toe of the eroding stream bank. How can we determine when too much stabilization has a negative overall impact, such as possibly causing more erosion to happen downstream?
How can we determine that? Well, we have the benefit of like 10 years of a 10-year interval between, for example, image acquisition or LiDAR data acquisition, where we can see where a particular bank stabilization uh, structure has either been cut around. For example, we often see a lot of scour at the downstream end of bank stabilization structures. And so we can sometimes see that in retrospect after it's already happened. But I think it's pretty difficult to anticipate where those kinds of problems are going to happen. Now, how much rock? I mean, if you're really going to stabilize a bank, you probably need to get your rock or wood or whatever material you're using to try to stabilize the bank up to, at least halfway up to the bank full stage. But you can also use structures like bendway weirs or, um, veins or something like that try to direct the uh, the highest velocity part of the flow, the thalweg, away from the eroding bank and towards the center. I will say, though, that as soon as we do something like that, we start to eat away at the point bar. And so as a mechanism for trying to reduce the inputs of phosphorus, we might be shooting ourselves in our own feet by not just reducing the input of bank material that contains phosphorus from cut bank erosion, but also reducing the capacity for the opposite bank to store phosphorus.
I have a question here. I think that referred to a specific slide potentially earlier on. It asks, in comparing two aerials to detect erosion and deposition, what year aerials did you pick, and how many years of erosion slash deposition is that measuring?
So the study that Forrest did with his remote sensing tool used the orthophotos that included an infrared band from 2009 and 2018. So there were 9 years elapsed between those two. And his method really does require that we have at least some infrared band. So there are some limitations there in terms of what imagery will allow us to do that kind of assessment. Now, you can take any imagery and hand digitize banks and do essentially the same analysis. It's just really time consuming to do that. But that's still something that we can allow us to use different types of imagery and even go much farther back in time before the four-band imagery was available. We did do another analysis later on where we were really attentive to the discharge in the river at the time of image acquisition, because if we have more discharge in for example, the second set of imagery than we did in the first, we're going to have wider rivers during that second image campaign, and it's going to look like there was a lot of erosion when it's really not a lot of erosion necessarily. It's just that there was more water in the river. So we had a threshold where we selected imagery that happened on dates where the discharge was no more than 5% different. And we get pretty consistent results across different pairings of imagery when we use those criteria.
Okay, perhaps one final question here. Can you infer from your work that straightening meandering streams in order to farm up to the stream bank will nearly eliminate phosphorus sinks?
I would say it wouldn't eliminate if it doesn't eliminate the access to the floodplain, it would not eliminate sinks. But if we channelized, straightened, and levied all of our rivers, that would go a long way towards eliminating a phosphorus sink. And at that point, our rivers are just conveyances that move whatever we put into them, move them farther downstream. So I think that's a pretty a cynical potential case, an end case, but it's an interesting thing to kind of use as a thought experiment.
Okay, well, I think that gets to most of the questions from today's webinar. If you have any additional questions for Pete, we happen to miss your question today. You can contact him directly at pmoore@iastate.edu. That's PMOORE, like the surname Moore. So Dr. Moore, thanks again. We're very appreciative of your time. To all our viewers, we will be back again next week. Thank you as well. That will conclude today's webinar. As a reminder, if you do need a CCA, CEU, please email Elena Whitaker. That's ALENAW@iastate.edu by 5 p.m. today. And with that, thanks again to everyone for attending, especially to Dr. Moore for presenting. I'll go ahead and I'll end the recording of this session. And thanks again, and have a great rest of your day, everyone.